Hello everybody, let's go ahead and get started with mechanical equilibrium. You should be taking notes throughout this PowerPoint. The big idea with mechanical equilibrium is pretty simple. An object in mechanical equilibrium is stable, we're going to talk about that word a few times today, without any changes in motion, and without changes is very important to mechanical equilibrium. So first off, we're going to talk about force. A force is a push or a pull. As you're taking your notes, I think it would be a great idea to highlight any words that I've highlighted because those are going to come back pretty often throughout this unit. So generally when we draw forces, we use arrows, and we always draw those forces in the direction of the push or the pull. A force is needed to change an object's state of motion. Again, that change is very important. If there is no change to an object's state of motion, then all of the forces are balanced. Now, there are three ways to change an object's state of motion. Pretty simple. You can make the object speed up, you could make the object slow down, or you could change the object's direction. And anytime there's a force present, that's what happens. When you drop something in a gravitational field, gravity causes that object to speed up. When you turn a curve in your vehicle, friction keeps you moving in that circle. If there were no friction, you would go in a straight line. So the force of friction allows you to change direction and complete that circular turn. Also, if we keep the example of your vehicle, if you're driving in your car and you slam on the brakes, that's another type of frictional force that causes you to slow down. So forces are needed to change an object's motion. And again, you can speed up, slow down, or change direction. Now, sometimes you're going to have a lot of forces on a single object, and the combination of all forces acting on an object is called the net force. It's like the overall force. When forces are in the same direction, they are added together. So let's just keep going with the car example. If my car is in neutral and I'm pushing it, I'm going to apply so much force, and then if someone else comes beside me and pushes with me in the same direction, then our force adds together and allows that car's motion to change even more. Now, if I am pushing on the car and someone comes and pushes in the opposite direction, those forces would subtract. Okay, they're not helping me at all. It's making it more difficult for me to get that net outcome for the car to move. It would be like trying to push the car up the hill. I'm pushing in one direction, and gravity, the Earth's pull, is doing as best as it can to push in the opposite direction or pull the car down the hill in the opposite direction. We'll look at finding net force here in just a minute. Sometimes you could have a combination of both. You could have two people trying to push a car up the hill and gravity's trying to pull the car down the hill. So the people and the earth are working in opposite directions. In this case, we have a muscle man here pulling with some force upward, or an upward push, and then we have the Earth's pull, okay, also known as gravity. And if those are equal and opposite, then there will be no motion. So here we have this upward force is equal and opposite to this Earth's pull. So that tells us that these forces are balanced. So there's no change in motion for this guy. He's just holding the weights. All right, so let's focus on finding the net force. This is where we're going to do some basic adding and subtracting. Here is one example. So here we have the applied forces on this box. Now again, it's very important that we have drawn all of our forces represented as arrows. And if one force is supposed to be bigger than another, it's supposed to be to some scale. You want to make it look bigger. So here we have 8 newtons pulling to the right and 3 newtons pulling to the left. Because those are in opposite directions, that tells us that we need to subtract those forces. Now, one rule that I always use when I am finding the net force, I always take my right force and subtract it, or I always do my right forces minus my left forces. Okay, you always want to look at your positive forces first. We could say anything to the right, because in physics, anything to the right, and I guess my video is wrong, that way is right for you guys, anything to the right is positive, just like in math. Okay, if you look at x and y axis, everything to the right on the x-axis is positive and everything to the left is negative. And we can treat that the exact same way in physics, and if you do that, that's going to help you a lot. So we have 8 newtons to the right and 3 newtons to the left. So we would say that 8 is positive and the 3 is negative. So if we add all of our forces together, we're finding the net force, or the combination. We have 8 newtons plus a negative 3 newtons or minus 3 newtons equals 5 newtons. Now, we want to make sure we have an ending direction for that overall force. Because the 8 newtons is larger, we can say it's winning. So the net force is going to be to the right. We have 5 newtons to the right. Because we use positives and negatives here, our answer, if it's positive, that means the force is to the right. All right, so let's look at another example. Here we have 2 forces, the same 8 newton and 3 newtons, but the 3 newtons has switched sides. So now they're working together. Because these forces are in the same direction, we should add them together. Both 8 and 3 are pointed to the right. That makes them both positive. So when we find our net force, we can say 8 newtons plus 3 newtons equals 11 newtons. And again, both of these are pulling to the right. Direction is very important. So we have 11 newtons to the right. All right, another example here. Now this one's a little different. Here we have opposite directional forces, just like we had here. But notice that the 5 newtons to the left is actually larger than the 2 newtons to the right. So I'm going to show you how I would do it first. I always do right minus left to find net force. 2 newtons is positive. This 5 newtons is going to be negative. So I say 2 newtons minus 5 newtons equals negative 3 newtons. Now what does that negative indicate? The negative tells me the net force is to the left. So here I have 3 newtons left over pulling to the left. Pretty simple. Now, if you want to do bigger minus smaller, I wouldn't recommend it because I always go right minus left, but you can. You can say, well, if 5 newtons is this way and 2 newtons is that way, it seems reasonable that 3 newtons is going to be left over. The one important thing is that you always write direction with that. Here, the negative tells me the direction. Here, I have to actually write the word left. So again, when they're in opposite directions, we just subtract. Okay, let's look at, I think, 2 more examples. Here we go. So this time we have a box with 4 newtons to the right and 4 newtons to the left. This would be, you're both pulling on the object with the same amount of force. There will be no change in motion. There will be no net force because 4 newtons minus 4 newtons equals 0 newtons. Now let's go ahead and talk about a newton. A newton is basically just our scientific term for weight or force, which we normally use pounds. Okay, but we need to get in the habit of using newtons because that's the SI unit for force. And so 1 newton is about 2.2 pounds. Just to give you a reference. Okay, now here's a combination. You can always do problems with lots of forces on these objects. So let's find the net force. Here we have 6 newtons to the right, 3 newtons to the right, and 4 newtons to the left. If I want to find the net force, I'm going to say positive 6, positive 3, negative 4, and I'm going to combine all of those together. Okay, these are, I'm going to do the 6 plus the 3 first. 6 newtons plus 3 newtons. Both of those are positive. This one's pointing to the left, so that means it's opposite direction. I need to subtract 6 newtons plus 3 newtons minus 4 newtons equals a positive 5 newtons. And that positive 5 newtons tells me that force is going to be to the right. So I get 5 newtons to the right. And I draw that with an arrow. It is very important you draw your net forces with an arrow because that's called a vector. And we're going to look at that here in just a moment. So another thing you might want to do is you can take 6 newtons and 3 newtons and draw and represent 9 newtons. And then 9 newtons minus 4 newtons. You're left with 5 newtons here. Guys, let's look at tension and weight now. So these are just two forces that are good to know. When you hang an object from a spring scale, and in the classroom we will look at different spring scales, and I'll show you some different spring scales in our lab tomorrow. But this is called a spring scale. It measures newtons or force, and we know that gravity pulls on everything. The earth pulls on everything. So when we stretch that spring, or anytime you have a stretching force, it could be in rope or fabric, anything that can really be stretched, your muscles even have tension. This force called tension. It's a stretching force. And the weight of the object is the earth's pull downward. Now, spring scales are used to determine how much the earth pulls downward. And so when you measure something with a spring scale, you want to hold it still, because if you hold it still, then we know that this up force, there's no change in motion, which means there's zero net force, because remember, a net force requires a change in motion. So since there is no change, we know that the spring scale tension force has to equal the weight of the object. These two forces have to be equal and opposite. Okay, so here's just another quick example. Here we have a spring scale that we use in the classroom. And here I have, this is 1,000 grams. It is 1 kilogram. That's how we measure mass. But I know that its weight should be somewhere around 10 newtons. And we'll learn how to find the weight of an object later on. But now here's a spring scale. Let me see if I can get this where you can see it. And if I hang this on it, you'll notice it's about 10 newtons if I hold it still, if there's no change in motion. Now, there will be a net force on the object if I try to accelerate it up. We'll see, or make it speed up. Remember, that's one way we can change force. If I try to make it speed up, then we see this arrow shoot this way. Okay? There becomes a larger net force. But if I just want to know the weight of an object, then the tension in the spring scale, if I hold it still, will equal the weight, or Earth's pull, also known as gravity, downward. Okay, those forces are going to be equal and opposite directions. And remember, when we're trying to find the net force and things are in opposite directions, we subtract to get a net force of 0. All right, let's look at our next slide here. Okay, so force vectors. We're going to start by, so a vector is an arrow. We've already been drawing arrows when we look at force vectors. And it's an arrow that represents the magnitude or the size. You know, vector said magnitude. So we're talking about how big. If you talk about a magnitude of an earthquake or something, it's talking about how severe, how big that earthquake was. But they have size and a direction. Okay, when we talk about a force vector, that arrow is going to point in the direction of the force. And the length of that arrow, the size of the arrow, represents the magnitude of the force. That's why I said it's important to draw bigger forces with bigger arrows and smaller forces with smaller arrows. Now, a vector quantity is basically any number or variable that has both magnitude and direction. So, for example, when you're talking about your velocity, okay, or moving somewhere, you can't fully describe that motion without saying, I went this far, this is how far I moved, that was the size, and then the direction. So if you think about ships, they use vectors to understand their displacement and where they're going. They have to say a certain degree that they are headed in and how fast the ship is moving. Planes, when they have to deal with velocity vectors and wind vectors. So if a plane is going in one direction and the wind comes at them in another direction, that direction is very important to understand, or the pilot has to know the direction of that wind in order to be able to adjust the course of the plane to get to where it needs to go. So in those cases, direction is important. So a vector quantity is just a quantity where direction is really needed to fully describe that number. On the other hand, a scalar quantity, size is only needed. Direction is not needed. It can be described only by the magnitude. So here are some examples. If we're talking about vectors, there's force, because we always want to know what way we're pushing or pulling. Velocity, generally you can say, I'm going 5 miles an hour, but that doesn't fully describe the motion. To fully describe the motion, you have to say I'm going 5 miles an hour north, 5 miles an hour in some direction. And then we'll learn about acceleration and momentum later on, but those are also vectors. Scalars can be a little tricky, but these are just some examples of scalars, and you'll see that you don't need direction to fully describe these quantities. So time, how long did it take you to do something? It took you, a couple minutes or 3 minutes. There's the magnitude. You don't have to add a direction to that to describe the time. If we're talking about temperature, how warm or cold it is, okay, you just give the number. You never attach a direction with temperature. So vectors, you have to have size and direction, magnitude and direction. Scalars are magnitude only. Now for now, the only vectors we're dealing with are force vectors. So just understand that force is a vector quantity. You have to draw that arrow in a particular direction. It's very important. You can't just draw the arrow any way you want. Okay? If I say there's a push to the right, then you draw the force vector to the right with an arrow showing the direction. And if it's a really big force, again, that's a longer arrow. If it's a small force, that's a smaller arrow. So pretty simple. All you need to know right now is we're going to be drawing arrows to represent force vectors. All right. Let's look at equilibrium. Mechanical equilibrium is a state where no physical changes occur. We've already said this. Okay? The object is steady. And we're going to use the equilibrium rule. The equilibrium rule is just written kind of fancy here. This is sigma. It's the Greek letter sigma, and it means we're going to add or combine all of our forces together. So this sigma F is net force. This says the net force equals 0. When an object is in mechanical equilibrium, everything is balanced. All of the right forces equals all of the left forces, and all of the up forces have to balance or be equal to all of the downward forces. So here we see these two guys walking on a plank. These upward forces represent the tensions in the rope, how much those ropes have to pull up to support all of the downward weights. This downward weight here is from the beam itself. And this downward weight would be the weight of this painter, and we have the downward weight of this painter. Now, if they're all going to safely stand on the plank, the net force has to be 0, because if there was a change in motion, if for some reason they exceeded the weight limit, then they would speed up towards the ground because Earth's pull would be more than the strings or ropes could handle. So let's think about this for a second when we're dealing with mechanical equilibrium. Here we have a gymnast, and she's holding on to 2 rings. Okay, how would the scale readings in both of the supporting ropes compare with her weight? Remember, her weight is Earth's pull. So how would the tension in each rope be divided because there's going to be a tension here and there will be a tension here. Now we know that all of the forces have to balance. So it seems reasonable to say that this upward tension is going to be the same as that upward tension because they're pointed the same way. So each rope here is going to have half her weight. Now, what if she hangs like this? Okay, there's slightly, if you're going to do that, if you're playing on, I don't know, monkey bars or whatever these things are called, the rings, you've felt this before. There's going to be more tension on one side than the other. So if you swing to where you're allowing more weight to be on the left ring, then it seems to make sense that this tension is also going to be greater because you're putting more weight on that ring. So in this case, the scale on the right would be less than half her weight because in this case, she's going to have most of her weight in this ring. All right, support force. So the force that comes from a surface supporting an object's weight is called the support force. Now, we know that tension is kind of a support force, but it has a special name because it's an object being stretched. This support force that we're talking about is when a surface supports the object. So in this case, the floor, or the scale even, is supporting the person standing on it, the person's weight. So we have a support force upwards from the floor, and the person's weight, the earth's pull on that person, downward. Now, the support force is always perpendicular to the surface. Now, perpendicular, remember, means it makes a 90-degree angle. So sometimes it's called the normal force, and that's just because in math, a normal line is a perpendicular line. So here, but you can just call it support force, that's fine. Here we have a 90-degree angle and the upward support force from the ground and a downward weight on the person. All right, here we have another example. A book is sitting on the table. When the book sits on the table, the earth is pulling down on that book, and the table is supporting the book. So if we're talking about the forces on the book, we have a normal force and a force of gravity, and those two forces have to be equal to each other because the net force is 0. Why is the net force 0? Because, again, no change is happening. Okay, suppose you stand on 2 bathroom scales with your weight evenly distributed between the 2 scales. What is the reading on each of the scales? What happens when you stand with more of your weight on one foot than the other? I want you to think about this for a moment and go ahead and write your answer. Go ahead and pause this video and write your answer. Okay, I hope you wrote an answer, but in the first case, the reading on each scale is going to be half of your weight. And you can even do this if there's 2 scales in your home. Generally, there's not 2 scales in a home. But if you put 1 foot on one scale and 1 foot on the other, and you're standing as, I guess, straight as possible, half your weight will be on each scale because your weight divides up. There's 2 support forces and only 1 pull of gravity on you. If you lean a little more to one side, then one scale is going to be larger. So the total support force adds up to equal your weight because the net force has to be 0. Now, if both of those scales read your weight, we wouldn't have balanced forces. All right, so here's just 2 terms you need to know. The first is static equilibrium. Static equilibrium is when the object is at rest completely, not moving. Pretty simple. If you think of I like to understand static equilibrium by thinking of a stagnant pond, okay, or stagnant water. That water is not moving. It's there's nothing about it. That's when you get the mosquitoes and all of that. It's just at rest, okay. This is actually, I don't know if you've ever been there, this is in Chattanooga, or right outside of Chattanooga in Lookout Mountain, Rock City. This is I'm not sure how big it is, but it's a ginormous rock that is just balanced on these two. It's called the Balanced Rock, and you can go see it at Rock City. It's pretty cool. But anyhow, static equilibrium is when the object is not moving. So there's no change in the object. Its net force is 0. It's in static equilibrium. The other is dynamic equilibrium, and that's when the object is moving at a constant speed. Okay, anytime the object moves at a constant speed, you have dynamic equilibrium. Now remember, there are 3 ways to change an object's motion, and when you change the object's motion, it's not in equilibrium. If you speed up, slow down, or change direction, you're not in equilibrium anymore. So to be in dynamic equilibrium, you have to be moving in a straight line and at a constant speed. Nothing can be changing about your motion. When you're in static equilibrium, you're just not moving. Pretty simple. All right, you guys, that's all for today. I know this was a long video, but these are the majority of the notes that we're going to be taking for this week. Take good notes, and please let me know if you have any questions. I'll talk to you later.